Hello guys, welcome back to my channel, Mason African Motives. Still working on moments for engineering science N3. So in this platform we are going to focus on the question paper which was actually written in July 2021. Yes, that is July 2021. So we had the question which is on question 2 on moments, and it carried a sum of 13 marks. So we want to see how we were able to obtain those 13 marks. So actually, if you're new guys to this channel, you can consider subscribing so that you won't miss any of the classes that we shall be having from Mason African Motives. Okay, so let's quickly rush through the question. There we are given to define the term uniformly distributed load on 2.1. Okay, take note there on 2.1, given define the term uniformly distributed load. Okay, so a uniformly distributed load, let me just try and reduce this. All right, something like that. Okay, so we've got a uniformly distributed load. It is a load that is spread evenly over the length of a beam. So take note, you'll be given a light beam, a horizontal beam, so that one will be distributed, that it will be spread evenly over a certain length. Okay, so that is what we have there. Then state the law of moments. This one, we've been talking about this law of moments actually if you've been following our classes, but still that is the definition there. It states that the system is in equilibrium when the sum of the clockwise moments about the turning point equals the sum of the anti-clockwise moments about the same turning point. That is what we have. So you've got clockwise moments and we've got the anti-clockwise moments there. All right, so that is what we had. And now let's just try and see the question that we had there. On 2.3, we're given that a beam is 6 meters long and is supported 1 meter to the left end and 2 meters to the right end of the beam. There is a uniform. Take note here, we've got a uniform of 12,234 kg per meter placed between the two supports. A load of 300 Newton is placed on both ends of the beam and 200 Newton is placed 1 meter on the right end of the beam. All right, calculate the reactions of the supports. All right, of the two supports. All right, let's do this, guys. Actually, we just need maybe just a diagram to indicate what is happening there, because it can be much clearer if we are having it from the diagram. So take note, this is what we are having here. That's our light horizontal beam there. So we are given that it is 6 meters long and supported 1 meter from the left end and 2 meters from the right end. So 1 meter from the left, which means just a certain distance from the left end here, there is a support. All right, so we've got a support here which is actually like 1 meter from the left end. So there is 1 meter there, and from the right end it is 2 meters from the right end. All right, so this is the right end here, so we've got 2 meters there in between. All right, so this is support, so it's supposed to be facing upwards like this. So this is what we are having, and that's something. We just put the dots there to indicate that we got nothing there, but just a distance in between. Okay, there is a uniformly 12,243 kg per meter placed between the two supports. Okay, so it is placed between the two supports, which means we've got a distributed load here between the two supports. There's a distributed load there. All right, so remember guys, there's a distance here which is 6 meters in between. The beam is actually 6 meters, so which means we have got 1 meter which we have used, 2 meters, so 1 plus 2, which is going to give us a 3. So it means in between the two supports, in between these two supports here, we have got a distance of 3 meters. 6 minus 3, which is 3. And we have got a distributed load which is going to be distributed in between. So we are going to calculate the force of that distributed load. So in this case, what is it going to be? All right, take note, The first thing here, we are not given the force, but we are given, this is mass kg per meter. So we are given mass per meter. This is what we are given, which is a 12,243. So this is 12,243 kg per meter. So we are supposed to calculate the force there, and which is the weight actually, because this is actually facing down. So we need the weight component for this mass. So the weight there is going to be mg, which is mass times the gravitational acceleration. So it's 12,243, which is the mass times the gravitational acceleration. We know that this one is 9,8. All right. So if you are to multiply this, you are going to obtain 119,9814, whatever that you're going to have there. But just avoiding working with the decimals there, let's just round off to the nearest whole number, this one. So it's going to be a 0 here, because this is 9. Giving this is going to give us a 0. You give 1 here. So 1 plus 1 is now a 2. So it will be 120 Newton per meter. Take note, it's mass per meter. So this is going to be the weight component, which is the force per meter again, because it's a distributed load. But now we want to change this distributed load to at least have a concentric, where we shall have this part here. So how can we change this distributed so that we can have a concentric load? We are going to multiply, because we've got a distance of 3 meters in between. So since it is 120 Newton per meter, so we are going to have a force now of 120 times 3 meters. Okay, so this is going to be your equivalent force, which is 360 newtons. All right, so that is our equivalent force here, 360 newton, because it's per meter. We are given a certain force per meter. Okay, so we are done with the uniformly distributed. We move on to this point. A point load, we are given another point load. 300 Newton is placed on both ends of the beam. Take note, on both ends. And the ends of the beam, we are talking about the left end. Remember, there's a certain distance from the left end and a certain distance from the right end. That is where we have a point load of 300 Newton. So we've got a point load which is facing downwards here of 300 Newtons on the left end, and on the right end here it is also facing downwards on the right end, like this. Same force or same point load, which is 300 Newtons there. All right, so that is what we are having actually. So let's see the other part. Take note, that is end. That is another part now. And a 200 Newton load is placed 1 meter from the right end of the beam. From the right end. So we've got 200 Newton placed 1 meter from the right end. This is our right end. So we've got 1 meter from the right end. So we've got something like this, just in between here. All right, this is what you're going to have, and this is 200 Newtons actually. So we've got 200 Newtons here placed in between 1 meter from the right end. So this is the right end. So there is a 1 meter distance in between these two. We've got 1 meter, but remember that previously this whole distance was 2 meters. So which means you can separate here to have another 1 meter to give you 2 meters, like that. Okay, so I think everything about the diagram or about this information is now represented on the diagram. That is what we have now. So the question is for us to calculate now the reaction of these two supports, which is the supports that we are talking about is the one that I indicated L, and this one I indicated R. All right, so using our the laws of moment, with the ones that we talked about sum of clockwise moments equal to anti-clockwise moments, that is what we are going to work with. Okay, so here I'm going to work with anti-clockwise. Okay, so taking moments, let's see where we are going to take our moments. So taking moments about L. I'm going to start with L. All right, so you're going to take moments about L, which is this support here, so that we can find the value of R here, which is the support R. Okay, so if we are to take moments about L, we are going to see that from the sum of moments, this, because this is my reference, so I'm going to start with this. See, as you can see, R is moving in this way, which is anti-clockwise. Remember, this way, that is anti-clockwise. Then this direction, that is clockwise. That is clockwise. All right. So since this R is moving in anti-clockwise, I'm just going to use my formula as sum of the anti-clockwise moments is equal to the sum of the clockwise moments, or you can just use this is equal to this, whatever way that you want. Okay. So since R is going in an anti-clockwise here, as you can see, R is going this direction, which is anti-clockwise. Okay. So which distance do we have from R there back to L? So as you can see, we've got a distance of 3 meters. So it's 3 times R there. 3 times R plus, do we still have another one in the anti-clockwise? Okay. Let's see, guys, properly here. If we are to place a part here, this is our support L. You'll see that this R is moving this direction, which is anti-clockwise, which is the same thing with this force here, because it's going this way, and we still, are you seeing, it's still maintaining the same way, so it's still in the anti-clockwise. So we are going to add this, which is 300 times 1. We are going to add it to this one because it's still in the anti-clockwise. Okay, so it's 300 times 1. Then we are going to move to the clockwise now. So the clockwise, if you are to cross-check, all these forces, they are moving in this direction, and this direction is the one that we said clockwise. So this one is moving clockwise, clockwise. So all these, we are just going to take them in the clockwise. Okay. So what is the distance in between here? Remember, this one is a distributed load that we had, so it's going to divide into 2 the distance that we are given of 3 meters. So 3 divided by 2, that is 1,5, and here you have got 1,5. All right, so this is your distance because of the distributed load. So it's 300 times 360 times 1,5. Okay, that's force times distance. 360 times 1,5, force times distance, plus we still have another one in the clockwise, this one, because they are on the same side, so which means they are in the all in the clockwise. So it's 200 times the distance between, as we can see, this is 3 meters, and here there's a difference, there's a 1 here, so it's 3 plus 1, which is 4, so it's 200 times 4. 200 times 4, plus we still have another one, which is the last one, which is 300, and the distance here we've got 3 plus 2, which is 5, so it's 300 times 5. That is the distance there. All right, so this is what we are going to have. So let's see, guys, what we are going to have. Let's just try and combine everything. That's 3R here plus 300 times 1, which is 300, is equal to, you combine this, you're going to obtain 540. If I'm not mistaken there, that's 540 plus, you multiply this, which is 800, plus 300 times 5, which is 1,500 actually. All right, so that's 3R plus 300 is equal to, you combine these, you're going to obtain 2,840. Okay, so let's just transpose this to the right hand side. It's going to be 3R is going to be, you subtract 300. All right, so if you subtract 300, you're going to obtain 2,540 in this case. All right, then divide by 3 by 3, your R is going to be 846,6666, something like this, and you're going to end with a 7 there. So rounding off to 3 decimal places, depending, or you can just put to 2 decimal places, maybe it's gonna be fine. 8,46 846 comma, we got 1 2. Since this is 6, it's gonna change here to a 7, so it's 6 7 in Newton. Okay, since the other forces were in newtons, so this is going to also remain in newton. If they were kilonewton like this is going to be in kilonewton also, but these were newtons. That is why it has to remain in what? In newtons like that. So that is what you're going to have there as a reaction of the support R there. Then so it means our R is now there. All right, 846 comma 67. This is our R there, newtons. All right, so we have to calculate L now. So we can choose to work with the moments about R now to calculate L, or you can use maybe upward forces equal to downward forces, depending. Okay, so let's see, guys, moments about R this time. So these are moments about R, which is, this is our R here. So still using the same concept. If you were to cross check now, from R now, L is actually moving in this direction, which is L is in the clockwise. So I'm going to use clockwise here since L is moving in the clockwise. Okay, so I'm going to use sum of clockwise moments to be equal to the sum of the ones that are in the anti-clockwise. All right, so clockwise. Why? Because we see that this is our R here, guys. As you can see, as L is moving, it's going this way. This is your L. It's going to go this way, and this way it's maintaining the clockwise moment. Okay, so it's going to be L times 3. There's a distance of 3 there, so it's L times 3, which is actually 3 times L. Okay, do we still have anything that is in the clockwise, or anything that moves the same way as this L is moving? This is what you're supposed to ask ourselves. Okay, we are talking about R here. Okay, and this is our L, which is moving this way. If you are to cross check, this L is moving the same as these two forces here, because this 200 is going to move this way, which is still is in the clockwise. The same with 300 is moving this way, which is still in the clockwise. So we are going to add these two to the L, because they are moving in the same direction, which is the clockwise. Okay, so we've got 200 back to the R here, so it's 200 times 1. Okay, so we're going to add this 200 times 1, plus we move on to 300, and there's a difference of 2 here, 2 back to R, so it's 300 times 2. 300 times 2, like this. All right, so that is what we have on the clockwise. Then we move on to the anti-clockwise. So which ones are moving in the anti-clockwise? Which one do we refer as the anti-clockwise? Remember, anti-clockwise is this direction. So which one are we talking about? 300 is moving this way, 360 is moving this way. So these are the two, 300 and 600. All right, so 300 back to R here is 300 here. We've got 3 and 1, so 3 plus 1, that's 4. That is the distance, so it's 300 times 4. 300 times 4. Okay, and we also have 360. 360 back to R here is 1,5, so it's 360 times 1,5. Okay, 360 times 1,5. So do you say that once you have the diagram, everything is going to be easier for you now, because you've got the diagram? That's how you actually work out these. Okay, so 3L plus 200 times 1, which is 200, plus this one is going to give you 600. Okay, so this one you just do the same, which is 1200 plus 360 times 1,5, which is going to give us a decimal there. Let's just see what you're going to have. Okay, so this is actually 540 here. All right, so if you combine these, okay, then you just try and combine the two there, which is going to give you 800. So it's 3L plus 800, which is going to give us 1740. Yeah, 1740 there. So transpose 800 is going to be minus 800 here. So 3L will be equal to 940. Okay, divide by 3 by 3. So L is going to give us a decimal again, which is 313,33333 until the end. So just to two decimal places. The first one we rounded off to 2 decimal places. We are just going to use also 2 decimal places so that it can actually balance well. Okay, so this is be our reaction L. So that is the idea there. All right, so that is our L, our diagram. Please don't mind this diagram. Okay, this is 313.33. all right, Newton, like this. So that is what you had there from the information that you asked to calculate. So I think we saw, so you can actually prove this by working with upward forces equal to downward forces. You are going to obtain the same thing there if you actually prove it. Okay, then let's move on to another question. There we are asked to draw the shear force. Draw a shear force diagram showing all main values. So we need the main values of the shear force diagram. Okay, so we actually know that from the shear force diagram, this is what you're going to have, guys. I want you to understand this in a simpler manner. Okay, this is what you're going to do. We're going to just draw our line like this. So this is actually okay, I think it saved, this ruler saved us. Okay, so this is actually 2.3, that's 2.32. So this is actually 2.23 there. Okay, so now I want us to see something here. If we are to cross-check this, it's actually going downwards. The first part, which is actually at the far left side, at the end of the left side, is going downwards because it's a point force. So you're going to go downwards 300 newtons. Okay, just a normal scale. So it's actually like you are starting at a 0. This is what you're going to have. Okay, let me show you what you are supposed to do. You start at 0, okay, and this point force is going downwards. So what you do is that you subtract the force because it's going downwards. Okay, so you subtract 300 like this. So the moment you subtract 300, you're going to obtain minus 300. So that is the idea there. So this one is going to downward until minus 300. Very sorry, guys, I don't know what's actually happening with this thing, but let me just show you. So it's going to be somewhere there. Let's say this is our minus 300 here. So this is our minus 300. All right, this is the point that you're talking about. Then what happened? There is a distance in between 1 meter, and we've got a support which is going upwards. So first, let us talk about the distance here. So you're just going to move a certain distance here, just move a certain distance like this. All right, then this support is going upwards, but how many units up? Whatever, everything that is pointing upwards, you add. So you're going to add 313,33, okay, to this number that you are now having, this one. So you're going to add minus 300 plus 313,33. Okay, so this you can actually use your calculator. Okay, so you're going to obtain something like 13,33. So you are now at 13,33, which is a positive. So this one is going to be a positive. So this is the support that you have added, and it's a positive. So this one is going to go upwards, okay, up to 13,33 upwards. Okay, so let's move upwards. Remember, this is at 0 here, so upwards, which means it's going to be above this line, above the line. Okay, so 13,33, we can just do an assumption. Let's just say it's at this point. Let's say this is where we have our 13,33 at this point. So this is our 13,33, this point here. Okay, what happened at this point? There is a distributed load, okay, in between for 3 meters. So you're going to subtract, because it's pointing downwards, 360 Newton. Okay, so you're going to subtract from this number, because it's point, that is where we are now. We are now at 13,33. We subtract the distributed load, which is going downwards, of 360. So we're going to subtract 360 there. Okay, so what are we going to obtain there? We're going to obtain negative 346,67. This is the value that you're going to obtain. As you can see, it's a negative, so which means it is going to go downwards up to that negative, and this is, take note, minus 346, which is going to be below this number, because this is minus 300. Okay, and the distributed load, we know that is going to be drawn like this. That's how you indicate a distributed load in a slant line like this. So you're going to slant, okay, until a number which is actually below minus 300. Okay, because this is minus 346, minus 346,67. This is where we are now at this point here. Okay, what happened at this point? Let's see what happened at this point after this. As we can see, straight after, just after the distributed load, there is a support R here which is going upwards, and we said anything that goes upwards is a positive. So we are going to add this to where we are now, and we are going upwards. Okay, so where we are at this point here, minus 346,67, we add 846,67. Okay, so if we add this, we are going to obtain 500 there. That is what we are going to obtain. We are going to obtain 500. So if it is 500, which means it is going to go upwards more than this, because this is 13, so 500 is going to be upwards. It's a positive, it's above 0 there. So we are going to go straight upwards, because it's a support there that we just added. So let this go upwards straight. All right, it goes upwards maybe to that point. All right, so this is where we are having our 500 there. Okay, that is where we are now. Okay, take note, guys, what happened after that. After that, we are at R here, which is the support. We have indicated the support. There's a distance between now. So this one, there was no distance in between. That is why it goes straight. But this one, there's a distance in between. So any distance you indicate with a horizontal line. So you're going to indicate to show that there was a distance which was in between. So this is the distance here. Let's just indicate like this. All right. So what happened after that? After that, we are going to go downwards. After 1 meter, there's a point load of 200. So this point load is facing downwards, and I told you that anything that faces downwards, it's a negative. So from where you were, you're going to subtract 200. So we're at 500, we subtract 200, which means we'll be left at 300. Okay, so this is going downwards up to 300. This one is going downwards up to 300. Okay, so let's just assume 300 is below this, just this point. Okay, so let's say this is our 300 there. So it is going to go downwards up to 300. All right, then what happened after that? Okay, there's also a distance here in between of 1 meter. So we indicate that distance, just a horizontal line. So this is 1 meter like this, just a horizontal line. Okay, then what happened after this distance? There's a point load which is actually facing downwards, a point load here of 300, and we said any point load we have to subtract. So we are going to subtract the point load. We are at 300, so it's now 300 minus 300, which is going to give us a 0 there. So take note, we started at 0, we are going to end at 0. If it is a distributed, so 0 is always here, like here, that's your 0 here, that's your 0. So which means you are going to just draw this line straight to that point like this until a 0 there. So that is your shear force diagram, guys. That's your shear force diagram. Okay, so guys, I think you will now understand the shear force diagram, because from the other classes that we had, actually, yes, we talked about this, but it wasn't that much clear, and I think I had to make more work so that you can actually understand, guys, what is actually happening here. So I think from this question you can use this concept to answer other questions also. All right, then the last question is determine the maximum and minimum shear force from the diagram. Okay, how do I determine, or how do I find the maximum and minimum shear force diagram, or on the maximum shear force from the shear force diagram? Okay, so these are the forces which are taken when we are having at 0 points, when it crosses actually the line that is the horizontal axis at 0 points. As you can see, this is our horizontal line. Okay, so this force here, I mean this from the shear force, this point here, it is where it has crossed the horizontal axis, and also here it has crossed the horizontal axis. But as you can see, this one is exactly so, so there's nothing here because it's just a 0 there. So which means from these two forces that we are having, which one is our maximum and which one is our minimum? So the negative, guys, is just for direction, to say that we are going in the negative, but we need the magnitude. So the magnitude is 346, which is bigger than this 13,3. So which means our maximum is 2.23, I guess 2.23. so our maximum value here, which is the maximum shear force, is going to be the one with the bigger value, which is 346.67 Newton, and the minimum is going to be the one which is the smaller. So it's not about the sign, it's about the number, because first we are talking about the magnitude part is the one that we are referring to. So this one is 13,33. So you have got 13,33, which is in Newton. So this is what we had from this question. So as you can see, guys, that's how they ask these questions. So what you need, guys, is to work with more question papers as you revise towards exams. As you revise towards exams. So as you can see, that was the question there, having 13 marks all in all. So guys, that's it from Mason African Motives. For any questions and for any calculations or methods that we might need to understand, let's talk on the comment section so that we might know the areas that we can actually work on, or the methods that we can maybe want me to work on. Maybe that's the method you understand, maybe it can be much clearer or much better. So that's it, guys, from Mason African Motives. Till we meet again.